Okay. It's already okay. Actually, we can move this a little so we more space for. So you have enough space, right?
Yeah, I have plenty of space, yeah.
Perfecto. For everyone.
Linear transfer.
Any.
Watch the
Well-
chairs.
And we can, but.
You ready?
I don't know.
I mean, it's technically time. We can wait.
Yeah,
Yeah.
we always wait a few minutes.
No, he doesn't have the suggestions.
But it's a linear tree.
Oh, okay.
Figure out the difference.
Yes.
Oh, yeah, fine, Chris.
Yeah,
Okay.
yeah, it depends on the.
Oh, and there is fresh coffee in there if anyone wants to get coffee before he starts.
Oh,
I
okay.
mean, well, I-
Might need it. I don't
Chop,
know.
chop.
Might need it.
Coffee will
Yeah.
help, yeah.
Chop, chop, because we know it's supposed to be, right?
right.
Nobody will stop you.
So it's
Every time there is no coffee, everybody complains.
But if there is coffee,
Yeah,
then no
nobody-
one wants
yeah.
coffee.
Nobody wants it. But that's one of the universe standard symmetries or something, anti-symmetry. So what was for Teresa, you think the most disturbing thing? Oh,
Huh?
you scared Teresa. If you go find Teresa, tell her that you already swallowed it down.
Oh, okay. Is that what that's what she left?
This
Some
is
people are
the,
very
this is the
sensitive.
sound, yeah.
Oh.
Some people would really, like
I
skin
didn't-
crawling nails on chocolate.
I didn't, I mean, I wasn't.
I can go fetch her.
Yeah.
But
I didn't realize it was that huge of a deal.
Where's Teresa's office?
I'll go.
You go? Okay.
I thought she looked at the Fano plane and she was like, I don't like the Fano plane for some reason that I've experienced in the past.
Shadesh, hey. Morning. How you doing? Okay, everything okay? All right. I added your students to the list. Who was it, by the way? Matthew? Matthew is here? No, and what was the other person? Oh, okay.
Take chance. Oh, good.
And,
Matthew will be there.
and here we have
Was Leonard
masked
sitting?
man.
Was Leonard sitting?
No, no, Leonard. Can move by.
Sorry. Come on, please.
See how much work has to be done to bring her back.
I mean, I'm not gonna be offended whether people show up or don't show up. It's their choice and
No,
Possibly.
I think it's always because Urek begins and he's so famous, so
yeah.
well,
he brings in a lot of attendance and then suddenly.
no. It's just middle of the semester, slowly approaching. People getting tired.
Which is crazy because I thought the semester just started.
Yeah, really.
And we're already.
A pain in the rear, sorry.
Already
It's
four
okay.
meetings.
No, I thank you for doing it because I also cannot. You know Leonard, not this Leonard,
Oh,
but
that's
Leonard from the Big Bang Theory. He's a cute guy, you know, Leonard.
Oh, that guy, yeah, I know.
I see, I always liked him. And then it was this, how's it, Comic-Con? And he talked to people, answered questions, chewing gum. I lost all my sympathy. for him.
Oh, me too. You know, it's not act,
Lack of the- Yeah.
it's not a lot of people.
Don't take it personal.
Oh,
please don't.
Some
I-
No, don't. I mean, it's.
I wish you'd have said the gum thing to me because I didn't realize that's why you left. I thought you looked at the Fano plane and you were like,
No,
oh.
no. I just, my personal preference is, that's your preference. I just don't wanna be around when people are doing it. Because I'm very neurodivergent and certain sounds kill me off.
Yeah, that's fair.
And so I didn't wanna make anybody's.
No.
It's okay. I'll make them stop.
Okay, so Okay, I'll get in frame here. Okay, I'm seeing myself there, that's uncomfortable.
Scary, right?
So, it's not scary, it's just uncomfortable. Okay, so what I'm gonna do is I'm going to start from bare bones scratch here, and we're gonna talk about just a set with a binary operation. I'm gonna build up a little bit of structure, and some of you might probably fall asleep during the beginning. But then I'm gonna talk a little bit about loops, different kinds of interesting loops, and some interesting open questions in loops that have been worked on for a while, and I don't know, somebody in this room could solve potentially. And then if I still have time at that point, I'll talk a little bit about projects that I've been involved in with non-associative algebra. So I'm gonna say we're gonna start with nothing. We're gonna start with a set S and a binary operation dot. I'm going to say this is a magma if it is closed. What does that mean? I'll give you an example. So I'll say magma is a set with a binary operation, and if we got 0, 1, 0, 1, just fill it in with all zeros. Okay, it's closed. It's a set with a binary operation, and the reason I'm building up from nothing like this is because it's a career goal for me to write a book where you teach abstract algebra starting with nothing, and then you spend time in other categories of less structure than groups, and you build up to groups. I think that'd be really cool. But this
Very poor bucket.
With values always zero, right?
Yeah.
the whole book. Okay, so what do we note here when it's not closed? If one of the zeros were 5.
Yeah, if something, yeah, if
On
you had
the side.
something not 0 or 1, it's kind of cool. You can do stuff with like magma rings. Actually, I worked on a project where we did magma rings. You extend by a basis. You use this as a basis, and you extend by some commutative ring. And so you can start here, and I'll use maybe I'll start this as the top of the structure, magma, and then we're going to move to the right here. And we're going to say that movement to the right is going to introduce associativity. So I'll just write associativity. And as we add the associativity, we get to a place called semigroups. Semigroups are a monoid that now we add associativity. We get semigroups. Maybe S,
Yeah,
that,
that's a choice.
SG, and now we have a set with a binary operation that needs to be, yeah, for all X, Y, Z. This, and so I'm not spending much time on this other than to tell you what a semigroup is. I'll give you a short example of a semigroup. A semigroup, what did I write down? I mean, 0, 1, 0, 1, 0, 0, 0, 1. That's associative. These are actually, it's not inherently, or not obvious why these are interesting immediately, but these have a one-to-one correspondence with finite state autonoma. So a lot of, people that do that kind of stuff are interested. I know that actually a project I finished working on recently, it was about these certain kind of graphs, power graphs, which I might talk about later. But the problem actually came from semigroups in the first place, and then other people had brought it over to groups, and then I worked on it for loops. So that's a semigroup. If we move down here, we'll say that that's adding an identity element of some sort. So we could add an identity element. We get to a monoid. That's how you spell monoid. And so if you add an identity element, you get to a monoid, which is just a semigroup with an identity. Notice here, no identity, right? Perhaps I won't write down an example of a monoid. I'll write down one because I got one down here. But I guess add identity. We'll get null for monoid, I guess. Set with a binary operation with associativity, and now we add on so that's it. We get the monoid, and I'm not even gonna write the example, but if we were to move here,
You mean EX equals XE equals X?
yeah,
Sorry, that's important.
that is very important, actually. That is very important. Thank you. But if we add here, what are we adding? Inverses or divisibility, you get to a group, right? I did that side. That's not really the very interesting side for me. It's called non-associative algebra I'm supposed to be talking about. So I'm gonna start again from magma.
Question?
Yeah.
Can one not be the identity there in the second example that you drew?
Yeah.
For zero though.
Yeah.
Yeah.
It is.
Sorry.
Okay.
I tried my best to pick ones that didn't have that were exclusively other things, but yeah. If we go to the other side though, which I think this is the far more interesting side, because the lack of divisibility gives a lot of, I guess it doesn't allow for a lot of the nice structures that we get to see over here in loops and quasi-groups. Maybe we'll see that something like certain kinds of loops actually have like Lagrange's theorem and stuff like that. So very powerful results we see in groups that we don't see over here. And so we'll say I lost myself here. I'll say Q is a quasi-group. A quasi-group has a binary operation, and you could people define it other ways. You define it with 4 operations, but in the spirit of building up a 1 operation algebra here, we're going to just do it with 1 operation. And so what we need is the idea of first we need closure, but we also need right and left inverses. And so that's important. We don't get inverses in the traditional sense that we have an identity, but we do have relative inverses. So for any A, B, and Q, we'll get something like A times, I guess there exists X and Y, where AX equals B, and so what do I want here? I want Y X equals B. So we get right and left inverses. We can get from any element to another by multiplication. This is the Latin square property, right? So if you were to if we were to write down a Cayley table like we did over there, actually I'll give you one for a.
Are you sure about the second equation? Don't you want like y a is b?
We want. Yes, Y A is. I'm sorry. I'm floundering.
So how would you call such a structure?
So you could call this the right inverse. You could call this the left inverse.
No, what's Q again?
Oh, a quasi group. Q.
And where in this diagram you're building? On the left side?
Quasi group would be here, adding
Okay.
the idea of some kind of divisibility. Although I don't want to call it divisibility because it implies we're dividing, but we could call it inverses, right?
left and right inverse.
Yep, the idea of a left and right inverse, and I think I do have a proper quasi group here. Example.
It's stronger than like a left or right inverse, right? Because you can get any element, right? Not just back the x, right?
Um,
Well, you're not assuming an identity element?
no,
Right,
no.
okay, that's-
So that's, and it's kind of interesting because we'll see in a minute, that example is gonna be really interesting, and I think that'll partially answer your question.
Okay.
So. I guess I better write it here, 0, 3, 2, 3, 1. And 0, 3, 2. Okay, so that should be a proper quasi group. I think I checked that. Meaning that it's closed. It has right and left inverses, so it's a Latin square, but it does not have an identity element. I hope. So what we're going to say here is these are really cool. This gives us a lot of interesting things. They're almost permutation like at that point, right? Because we see everything appear once in every row and column, but obviously not quite. But the interesting thing I was going to mention is if we do add an identity element, so we move down here, we add an identity element, we get loops. That's for me, the really interesting area which I care a lot about. And so we add an identity element and we get this example over here. And the interesting thing about this example, which I want to showcase, is there shouldn't be, I hope so. I usually spend a long time, I use finite model builders to build all of these for me. And you gotta be really careful when you're writing down the.
Camera can't see that more.
Oh,
I see,
okay.
yeah.
And so I think we're gonna look here, and what we're gonna find is that we do have our relative inverses and we do have identity. And one might think that because all we need to introduce here to get to groups is associativity, we might think that we are guaranteed, I'm sorry.
You're good.
Jackson,
You're good.
sorry. We might think we're guaranteed unique left and right inverses, right? But I'm pretty sure on this one, we look at 3 and we try to get to identity, identity 0. So on one side, we get 3 times 5 is 0. And then if we want to get to 0 here, we multiply by 4. So we don't have a right and left inverse guaranteed, which is something that's not intuitive. I think the first time I thought about it, I probably just assumed that there were right and left inverses. And actually, this is where I'm going to introduce my first loop property, I guess. And that'll be flexibility. Is it A or I? I don't know how to spell, but flexibility is just this, X, Y, X associates. And if you give a loop flexibility, you allow it to be flexible, then you can force unique right and left inverses.
What's a loop?
Yeah, did you define the loop or?
Oh,
Yes, it is.
so a loop was a quasi group and we just added the identity element. So now we have and the identity is necessarily a two-sided identity. And I'm putting
So
it.
that loop.
So what I was trying to showcase is that is interesting because you don't have the unique right and left inverse, but you still do have relative inverses from any element you can multiply to get to any other element.
So flexibility would be a special property some loops might.
Yeah, some loops might possess. And there's a lot of interesting constructions on how to build, a certain loop. And I'm going to show you exactly one, and I'm saving it for a more interesting class of loops. Let me see. I guess there's a lot of interesting properties like flexibility that'll introduce things that we do want.
What about X, X, Y also with brackets?
This is a really good question because that's called left alternativity. And that'll give x, x, y is x, x, y. And then we got right alternativity. Which will exactly what you'd expect, x, y, y, x, y, y. And so those, it's actually really interesting. I don't know if I'm the person to talk about this, but these three, left alternative, right alternative, and flexible, if you allow something to be a structure, a loop to be all three of those, you're very close to being a Mufang loop. And a Mufang loop can be thought of as a group with triality. And so its automorphism, triality is like the automorphism group admits S3 actions. And you can show that they come from these three properties.
And of course, famous octonions satisfy it, right?
Yeah. Those octonions are Mufang, which I'll draw out a diagram here in a minute. And yes, they satisfy all three of those. So I will go ahead, I guess, and then draw my diagram of interesting loops. This is a bunch of varieties of loops. I don't see Layla. I was hoping she'd be here, but Petter Vadishovsky, I'm sure I'm saying his name wrong, and J.D. Phillips proved in 2003 that there is this hierarchy of loops here, and so I'll explain it as soon as I'm done here. Oh. Um,
Are all these loops?
yes.
Okay.
You will explain the acronym.
Yep. I just wanted to make sure the ones that cross I always miss. So these are, I guess, called they called them loops of Bull, Mufang type. And each of these has defining identities. 3-power associativity, for example, that's this on the bottom. So that's maybe the bare minimum structure you could ask for with a loop. Remember, I said we're not flexible, we don't even get unique inverses. You could probably go more general than that and just ask that X associates with itself once. So that's 3-power associativity there. And then I've already told us about flexible left alternative and right alternativity. These are really cool because if you're working with, and this is a reason I think it would be cool to teach abstract algebra, starting with no structure and building structure up. Using combinations of two of these, you can do a lot of things that you might expect to be able to do in groups. So that's kind of cool. Using just these basic things, you don't need full associativity.
Ron, this from ML to FI, you can draw it without crossing on the left side. Is that right? Or you need it for something?
Okay, so I drew it the exact way the diagram drew it in the paper, and I'm pretty sure the way they drew it that way is because you could you can make a mirror plane through there and you can like dualize these. So like a right bowl has an associated left bowl. Left alternative has an associated right alternative. That's exactly the way as it appeared in their paper. Maybe it was a little bit neater, but yeah, if I were to draw it unprompted, and I guess I was here, but I would have put the FL in the middle because it makes more sense to me. But there's a whole thing in the paper about dual identities and how you only need to prove a certain number of these things because right and left, there's an associated left nuclear to a right nuclear. And so I've talked to 3PA, flexible, left alternative, right alternative, bowl loops. These right here, these might not seem all too important. They're a step on the way to Mufang loops, which Mufang loops are probably what most physicists have heard of. But I do believe that left bowl multiplication, and Sujesh, you can probably tell me if I'm right or wrong here, but bowl multiplication is used for addition of relative vectors in special relativity. So it's not associative vector addition in special relativity, and it behaves like a left bowl loop.
It is not associative.
Yeah.
Yeah, what is the actual property for a bowl loop?
Oh, okay, so the defining property for I'll just write down a left bowl loop here, is a XYXC. XYXZ is bracket S. And then, oh, it's an easy one. Okay. I like the ones that those are 1-5s. There's a naming convention for these identities. So all identities appear like this. They're fourth degree monomials with a repeated variable, and you just bracket them in different ways. And a lot of them reduce to things like this. Some of them reduce to just being groups. Some of them reduce to being extra loops. They're called extra because it's a little bit extra from the Mufang structure. And then so this is the left bowl loop. And then maybe I should write down a Mufang identity too, and then I'll talk a little bit about the right-hand side, though I won't say much. The Mufang loop has so each of these has equivalent identities. That's just one you can pick. You can prove that the other ones are equal to it. But a Mufang loop, there's no way I wrote down the Mufang one there.
So does the loop have to do with the X repeating itself? It's coming back, or is there some significance there?
Why is it called loop in essence?
I do not know why it's called loop. There, I knew I had to have written that wrong because that was the Mufang identity. And so Mufang Y X Z. This one is outside bracketed. But that one's important because there are so many rich theorems here. Like I said earlier, Lagrange's theorem exists for Mufang loops. I actually met the guy that proved that at JMM, so that was kind of cool. And then, boy, take your pick, octonion multiplication. If you're to take the unit octonions and multiply that picture that we had up there.
Yeah, a lot of people see
Yeah,
that.
okay, yeah. So the picture that was sent out with it was the Fano plane. And if you take E0 through E7 to be the units of the octonions, you can follow the Fano plane there and get multiplication. And if you follow the arrows backwards, you get negatives. So that's kind of cool. And I think it's if you take the split octonions, so you take the units and their negatives, then you can make a 16 element proper loop from it as well. So On the right side here, what these ones mean is this is left nuclear square, middle nuclear square, and right nuclear square. What do those mean? That squares associate. So let me see if I can not look at my iPad and think about it. If we want a square to associate in the middle, we can put a y and a z or something. And we can do this, y, x, z, and we can just dissociate on the other side. So there we got a middle nuclear square. That means squares that occur in the middle associate. Left and right would be if you got a square on the left-hand side, it associates, or a square on the right-hand side, it associates. And so it's I thought it was super fun. I spent a lot of time during my master's degree on a project where we would take exactly what I was talking about with the magma rings. If we were to take a loop that satisfies this, or a variety of loop that satisfies this, and span it over some commutative ring, so you treat these you could essentially treat these elements, right, as your basis, and then take the span over a commutative ring. There is a little bit more work that needs to be done because this won't carry over. This identity doesn't mean the same thing when you add a second operation. You need there to be a bilinear form, right? So I'm not going to talk about that unless I get through all the loop stuff first, but you do need to do more work to these identities to make them work with a bilinear form. I guess now that we've gotten to Mufang loops, what do I have written down here? I guess I'll show you one famous construction of Mufang loops, and then I will give you, what else do I have? A couple big problems after I give you Mufang's theorem. So I guess, are there any questions about the diagram you read from? A group is not an extra loop. So if I'm a Mufang loop, that means I'm everything below it and not necessarily everything above it. So I don't know. I remember when I was working with Lindsay Kay, she looked at me and said, "These Hasse diagrams you're drawing are upside down." And I said, "I'm sorry, that's the way somebody else drew them, but that's the way they were drawn." So we got that.
I miss the anime, right?
Yeah, I'm not. Nah.
Oh, very good.
If time didn't exist, we wouldn't be sitting together.
I put most of this
We will
together while
spend time
proctoring
together.
tests yesterday. So, okay. So here's what I'm going to show you is orange chines construction. So the reason I'm showing you this is just to show you that there are ways we can build loops. I could show you a construction for a more general thing, but this builds a lot of Mufang loops, not all of them. But why do we want to show how you can build them? Because something like a group occurs really naturally, right? You can look at symmetries of something and hey, you got a group. And what we're actually going to do is we're going to use groups to build Mufang loops here. So we'll say if we got G is a group, and we got a C that is not one in the center of G, and we have an indeterminate U. Indeterminate, then we will make this structure M dot, where M is G union GU. And so we need to follow these multiplication rules. So just to make a little sketch here, if this is a Cayley table, like I've been drawing for those, if this is a Cayley table, these are group elements here. 1, 2, dot, 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 GN. And then we would relist the elements multiplied by the indeterminate u. So we got G1u dot 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 GNU. And we do that, going down to 1 GN G1U dot 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 GNU. And so if we follow the following multiplication scheme, what we'll get is essentially one of these is for each quadrant, right? So if we want G times H, that's going to give us GH. So that gives us that the first quadrant is literally just a copy of the group. If you want to cut it into quadrants, G times HU.
If you're using a star, do you mean the star to be the operation of M?
So
Because you have M.
G times H out here is going to give.
What do you mean by star?
What do I mean by star? I mean star is.
So you have two different multiplications?
Yeah, so G times H is everything occurring here. These are G, this is H, why not, or H and G. So we're multiplying these two things to get inside here.
It's the original group operation.
Yes, it's the original group operation.
Okay.
Now it's gonna be in there.
okay.
And then, so this
Star
one
is dot.
is GHU. So this is GHU right here. So that's going to give us this quadrant. But how are we going to evaluate that? We're going to read it. Is it HG dot U?
That would be kind of precise. G, comma, star brackets is a group.
Yeah, yeah.
Yes.
And H and G are both arbitrary group elements.
Yep.
Okay.
And so, I'm sorry. Then we'll get the third one is G times, what is it? Here's the third one, H. Yeah, GU times H. Is this G inverse U? And then our G U GU HU C, and that's where the C comes from. H inverse G. And so that's
So
Now this dot is what?
the dot is the attached element.
so what is HG in your second line? This is the group
So
here, HG, yeah.
HGU. So you can think of U being an attached element here.
Okay.
And so it's HG multiplied by this indeterminate. And so then this one's GH inverse as evaluated in the group multiplied by U.
all make sense.
Does U exist independently or is only as an attachment? Is there an element U that
So there is a real element U that you will multiply, but you can think of it as being attached.
okay.
So like every element here is just another element really, but we're renaming it. We're giving it a name. We're calling it G star 1 or something like that.
Okay.
I don't know if that could be more clear than G1U.
Not use star for two different things.
Oh yeah, I don't mean another star, but so yeah, this is just if you were to take it's really just a renamed element that we're attaching this indeterminate to.
And wait, can you explain again what C is?
C is just not identity in the center.
Okay.
Yep. So this won't work for a trivial center, right? But this creates a lot of interesting things. Okay.
It feels like this is backwards. Like all the stars should be dots and the dots should be
You're
stars.
correct. Or other way, you can fix it. The operation on G
That's
is the dot, the operation on M is the star. I think it has to be. And then you have an extra one, which is just append U to the end on the right or something,
Now I gotta.
I think.
Okay.
You guys are messing.
Just a formal variable, yeah, or something.
Yeah.
Get pale.
This problem is just formalism though. I think.
Yeah. Give me one. I just wanted to, because I swore I copied it right out of the thing. What's it called? I mean, I'm certain I'm wrong, but I also am just checking that I can copy something down correctly. Okay, no, I must have been in a completely different universe because they don't even use two operations. They use juxtaposition and dot. So they use juxtaposition.
The star is not now.
It's okay, we
Oh, you
understand
said
what's going
Oh,
on.
this is G. Yeah, you're right.
So yeah, we multiply this on the outside, get that on the inside. Yeah. Oh, we're through that, I think. I apologize. Okay. So what did I want to say about Mufang loops?
So this example of a movement group, that I mean, look,
Construction.
Yeah, this is, you can construct a bunch of them.
that's every movement group can come from some sort of group this way.
No, because we need a non-trivial element of the center. But this creates a lot of them. There's
a lot of them. No.
So for like, I'm trying to, let me see, for all of them that are under size 64, there's two constructions that can iterate all of them. And then after size 64, I'm not sure if somebody's proved you can do all of them, but there's at least 4 constructions to build ones that are bigger than 64.
Can every Mufang loop be constructed this way, like depending on a different group, or is that not the case?
That was the
Same
question,
question, yeah.
So
Same question, yeah.
yeah, I think no, not every Mufang loop can be constructed this way. Definitely not.
Okay.
Even at size 16,
Mhm.
there's ones you can build 2 of them from the quaternions, one using this method and then one using a different construction. So you can build 2 different Mufang loops from the same group.
But the other question is also ones that just aren't reachable at all with this kind of any of these approaches.
I don't
Just
know
cover
if
that
there's
they
an
don't
answer
cover
to
all
that.
possibilities,
Yeah,
which is fine, yeah.
That's the
Yeah,
question I thought you guys were asking, so I was asking.
no, I'm not sure if there's proven that there's a Mufang loop that we don't know how to construct. But here's something interesting, I guess, a little tidbit, that you can realize the monster group as the symmetry group of a very large Mufang loop, which I think is very cool. So there's a small.
How big is this loop? It's bigger than the group.
No, it's smaller.
Right?
Yeah,
That's
but it's still very large. It's still very large. And I think it's a page loop furthermore, which means it's like a simple Mufang loop, and simple Mufang loops can only be powers of 2. So 2 to the big power. So 2 to the big.
Interesting. So this means, So would it work for also other groups? You know that they are symmetries of some loops.
Yeah, I'm sure it would. Yeah.
Anybody already classified it? It's like what sort of groups do we get as symmetries of loops? Not yet.
I'm almost certain somebody's done that. Not anybody that I know their name. Yeah.
Cool.
So we've got this. We've got so I guess I'll just write down Mufang's theorem now. This is what Ruth Mufang proved in the 30s, and it was pretty interesting. Shows that they're not too far away from groups. So Mufang's theorem. So I will first say it in the way that you'll probably read it anywhere, because most people don't quote the original theorem, they quote a direct result of the theorem, which is a Mufang, I guess in a Mufang loop. Any XY generates a group. So XY is always a group in a Mufang loop. And that's the way you'd probably see it. This is capital M, and that's a property called diassociativity. And diassociativity is literally any two elements generate a group. But I will write down, I guess, the original theorem.
Is Mufang the minimal such structure? Like if you went to some, you had this diagram of all
Yeah.
of these structures, and if you remove some structure and no longer Mufang, is this false?
So that's a very interesting thing. There are structures that are Mufang or that are not Mufang that are diassociative. They weren't thought about at the time, but they're called automorphic loops. So every inner mapping is an automorphism.
So the answer to my question is no, Mufang is not. So I guess what you're saying is there are structures that are not Mufang, but do they have less structure than Mufang or non-comparable structure to Mufang?
I would say definitely less structure.
I see. Okay.
How do I say it? How do I think about this? And okay, let me think about an A loop. No, A loops don't satisfy this. So an A loop, an automorphism loop that is diassociative. If you're an A loop and diassociative, you have to be Mufang. Sorry, I answered incorrectly the first time. So is there anything less that satisfies this? Yes, but it would be not comparable, and I don't know if it necessarily has a name.
Okay.
But there are diassociative loops that are not, and there are automorphic loops that are not Mufang. But the combination of them, so both of them by themselves are weaker than just being Mufang. Because with Mufang, you also get other things like Lagrange's theorem and stuff like that.
Thanks.
And so I would just say the original theorem, I guess, restated. And this isn't really restated because this up here is a consequence of what I'm going to write down here. But when people refer to Mufang's theorem, they usually just say this. It's if you have any X, Y, Z that is associates in a Mufang loop. So if X, Y, Z such that this is true, then X, Y, Z generates a group. And it's not immediate or anything, but this is how you'll usually read Mufang's theorem. And so there are some things, right, that we can say we can't, since we don't associate in the same way that we do with a group, we cannot say so here I use the center of the group, right, for the horrible job of me presenting a construction, but the center of a loop is not the same. Because in a group we have associativity that gives us automatically things that are commute are in the center. In the loop we call, I guess this is another loop property, is a commutant of a loop. Call that C of a loop. And those are just so it's exactly what you would expect the center to be, I guess, depending on how you think about things, right? It's just the A that commutes with every element. So AX, XA for all X and L. So you need things like the commutant to talk about approved things. And then you call it nucleus. There are 3 different nucleus. There's a left, right, and center nucleus. And those are the sets that associate on the left and on the right. And so, you know, in a group to talk about the center, all you need are the elements that commute, right? But here we don't have that. We need to consider the right and the middle nucleus. And so we can call the nucleus the intersection of the left, middle, and right nucleus. And so then you can actually get a center of a loop. The way you can get the center of the loop, it would be you just take the intersection of the nucleus with the commutant. So I'm gonna say, there you go. There's a bunch of random information about loops and non-associativity. If you've got any questions and you somehow thought that was interesting.
I mean, I thought it was very interesting, but like, I'm kind of curious. I can totally see how you get back associativity, like if you're generating, but how do you get identity and inverses for Mufang's theorem?
So you're already a loop.
Yeah. Wait, do you get identity or inverses from?
So you what that diagram I drew in the beginning?
Yeah, maybe I can.
The loop automatically gets the first thing you get's the divisibility, so the inverses.
Yeah.
And then the second thing you get's the identity. Those are the 2 things that make it a loop.
Oh, I see.
And
I
then
see. Yeah, I forgot. Yeah.
You necessarily get the 2-sided inverse from this because anything that's Mufang, that diagram I had before, flexible was below Mufang, and remember flexible was what I said you needed to force the 2-sided inverse.
Mhm.
Furthermore, I guess, even better than diassociativity here, this is actually 1 step removed from this is what I've been working on, is power associativity. And power associativity just means x to the n is about this. X generates a group. If X generates a group, then you're power associative element. And if every element is power associative, you get a power associative group. And so you can probably use that in the proof of that. Yeah.
So can you visualize associativity on the table in the Cayley table? How will it look like if it is associative? Like
on a Cayley table?
Yeah.
I have not found a good way to do that. That's a hard check one. You just have to check. Because I don't know if there's a good algorithm for.
If you want some sort of visualization, all those like brackets inside brackets and so on, you can present in form of a tree.
Parse tree, yeah. Effectively.
Possibly. But you know, like a tree A and B, if they are inside the bracket, you put like loop
So
and with C, there will be another one and so on. So yeah.
So there's The associate on the Cayley table. So you've actually, so that's almost exactly what I'm currently working on. I'm working on a graph where if elements associate, you have edges between them. And so what I'm currently looking at is how, if you look at how many possible edges could be in or could possibly be missing in a structure that is power associative and not diassociative. Because in a diassociative structure, everything would necessarily associate, so. Or kind of. That's not exactly right, but for the graph I'm building, that is right. But for the
That's
graph.
very interesting because then if there is a sub loop which happens to be a group, you will notice that.
Exactly, they're cliques, yeah.
So I'm looking at that Cayley table over there, which is, you said Mufang, right?
No, that's just a loop.
Just a loop.
That's just
Okay,
a loop.
okay, gotcha. Never mind.
What were you gonna say though?
I was gonna say that's 4 quadrants that generate themselves.
Oh, really?
Yeah. So the
Oh,
first,
yeah,
the top left quadrant is all 0, 1, 2,
Oh,
and it's closed that
yeah.
way.
Yes.
But if you take any 2 elements that are not within the same quadrant, you generate the entire thing.
Yep,
Wow.
Yeah.
Okay.
Good observation.
You just looked at that the whole talk?
No, I looked at that like maybe a minute ago.
I made him put the camera on.
Yeah.
I give you credit
No,
for that.
because I was thinking that's I misinterpreted that was Mufang or misremembered, and so I was like, okay, I'm going to pick 2 elements from that and see if I can generate a group structure. And so I was looking at it. You don't get a group, but you get something interesting. You get like almost like small fields because they're prime numbered sets there. You get 3 elements, so you can regenerate all of them.
yeah.
That's interesting.
But no, the way you could see that that's not moving right is I think I said 3 doesn't have a 2-sided, yeah. But yeah, no, that is a pretty interesting one.
This
And
is
and I wish I could take credit for coming up with that, but when I want loops, I use a finite model builder called Mace4, and essentially you can give it a list of things you want, a list of things you don't want, and you wait a long time and it spits things out for you.
The ChatGPT give you also good answers. You want an example?
I'd imagine
I imagine it might.
I'd imagine
don't
it might
know.
give you some baloney too, though.
Now actually that was a funny one because I never gave you two problems. So I totally forgot. The reason I wanted to show you this was because a big problem in loop theory, and it's been worked on for a long time and nobody's been able to close it up, is when is the commutant of a loop normal, of a Mufang loop specifically normal? That's had a lot of work done. Just last year, JD Phillips, who's a big loop guy, his son published a paper about it, and I haven't read it all, but I can tell you from the abstract that he did not close it up.
Normal in like the group theoretic sense.
Yeah, exactly. Yep. And then the other problem is actually from JD himself, which is can there be oh boy, I better look. Otherwise I will forget. Is there a Mufang loop of odd order with a trivial nucleus? So only the identity associates of odd order. That's also unanswered. Is there a
With the trivial nucleus. So just the identity of it.
So yeah, there are the two questions I totally forgot to tell you about. But yeah. Feel like I got there in the middle of answering a different question, but sorry. Hopefully there was something interesting. If there wasn't, then
No, it
Well-
was very interesting. Yeah, thank you very much. You can still take some questions, right? Or-
yeah, no, I can answer whatever. Or I can try to answer
You
whatever.
answer those 2 questions.
Yeah.
So very quick now.
Oh, I remember why it came up now. Because my test for AI when I'm gonna truly be scared of AI is I always ask it to prove the commutant of a Mufang loop is normal, because I know it's not always normal. And it always does it, and it does it perfectly, and it's 100% sure that the commutant of a Mufang loop is normal. So.
But if ever it answers
If
no,
it
then you're in
ever
trouble.
answers no, then yeah. That's when I'll be scared. That's when I'll be scared.
I was trying to cheat and feed Math 101 questions to ChatGPT yesterday.
And
And
you do better
it
or
was
worse than your
wrong.
students, though.
It did worse, I think, than my students.
So last
was like, wow.
semester
Still
I had,
artificial stupidity as of now.
Well, I was hoping it could at least do 101 math.
so I had a student that it was the day before a break or whatever, and he's doing the cumulative homework and I'm sitting down, I'm TAing for 101, and I watch him 3 times in a row screenshot the screen, plop it in Gemini, screenshot the screen, plop it in Gemini, and he was not getting the right answer, and I thought it was better punishment to sit there and watch him and say anything. Any more loop questions? I will try my best.
I
Yeah.
have a general, okay.
Oh, sorry.
No,
Like
no, no.
when you had the whole family up, that was really cool. Do each of them, everyone, like, is there like a simple like Haley graph for all of them, or did some of them get like really big? If you had to like pick like a simple example for
Oh,
that
okay,
illustrates each
so
one.
you got a pen or a pencil.
Yeah.
Write down loops of Bull Mufang type.
Okay.
It was 2003, published in the Rocky Mountain Journal of Mathematics,
Okay.
and it's J.D. Phillips and Petr Vedishovsky, and you'll see all the defining examples there,
Okay.
and they're all of manageable size.
Okay.
Yeah.
Because it's really cool actually, like, you know, see kind of play around with them and see how they work.
Yeah, and it's super fun too. Like, if you're interested, sometime I'll give you like some of the things that I had to prove for my master's thing, and it's just manipulating those equations and to make them look like the other ones. It's just
You know, you've got toilet holding out on us
Perhaps.
with algebra.
That's 521.
Is it?
Is it 521?
No.
I didn't think there was.
Because
If you,
we've been
yeah.
held out on.
If you take some topology and especially knot theory, in knot theory, they
Oh,
use something
yeah.
which is called, what's it called? Quandle.
Yeah, Quandle.
Quandle is a
Yeah.
beautiful example of non-associative algebra, actually a loop.
Yeah.
Oh,
Quandle. And
Well, Quandles are not quite loops.
they're
no.
not loops, but they're
No.
non-associative.
Yeah, they're not because when I did my master's, the guy in the office across from me, his master's thesis was Quandles that are not Quandles. Yeah.
So this is, if you draw a diagram of a node on a paper, you can color things, like red, and the moment it goes underneath, you have to change the color into blue, and so on and so on. And with this number of possible such colorings, give you something like invariant of particular node. And people notice, hey, wait a second, we can make out of this an algebra. Algebra turned out to be Quandle, in satisfying some funny identities,
You're talking about mathematical knots?
Yes, yeah, of course. Oh, well, the same thing, like not missing
Yeah.
on your shoe, by the way. Did you notice? You're missing another one.
No, I tied it right just
Oh.
a minute ago.
I'm too late.
that's actually where I first heard about using 3D printers in mathematical research was about knot
Oh,
theory.
really?
So I believe it was number five.
Yeah.
Well,
But
I
solid.
believe
Oh,
on,
yeah.
I believe on,
Liquid
I
strength.
believe it was number files. They did an episode where the mathematician, he was making stuff that, they tried to use with like strings or other real objects and couldn't do it, but then they found a way to, at least on some of them, make it to point to one 3D.
Yeah, so you can.
Yeah, exactly. So then they found out a bunch more about knot theory.
Yeah, okay.
Here.
I did two remarks. Is it okay? So one is when you write your book, make sure that you say why it is called loop. the nasty answer could be because it's so difficult to find an application, you need a loop to find one. But this is not.
I think it has to do with the like identity element being like two-sided, and then like this is similar to like a path topologically.
No, there was I knew it was, but I don't remember now. But so one thing is that people actually very often comment that the whole 20th century in physics, it was mostly group theory for particles, for everything, symmetries, and so on. And such beautiful structures were never even, considered. And this is time to really look for this for physics. As physicists should look at those structures.
What was another thing? I can't remember. I read a paper a while ago and I told you about it and I can't remember, but it was multi-set algebras. So like, you take a loop ring and you take the tangent space of a loop ring and then,
okay.
Yeah.
Okay.
Oh, okay.
And another thing, if somebody's interested, sorry for bragging, I found a beautiful loop representation of addition of relativistic addition.
Oh.
And this is like a 2x2 matrices with quaternionic, entries and short paper. And since this is my paper, I can say elegant. I think I gave you a copy of this a long time ago.
Very possibly.
And then you threw it away. Yeah.
Okay. Most likely.
But
Never read it.
yeah.
That's what you should do though, physical copies, because then I can't just look at the email and say like,
I see. Okay.
I'm
I
doing-
can give. Okay. Oh, yeah, you can read it. It's super interesting. So the idea would be like to find other applications outside of the loop theory, things which happen to be loop, and what does it give you?
that might be somebody else's
Physics.
yeah. Because
It looked like this.
yeah, no. I don't know. I really like the just playing around with the equations and finding something cool. I'm excited to go to Savannah in March or whatever, and that JD Phillips guy will be there, and Petr Vedashovsky will be there, and
Do you already know them personally?
I know JD, and then I can't remember, is Edgar Gader gonna be there, and then
Oh, that Layla worked
Yeah. yeah, Layla would know, but it's gonna be really cool because I'll get a fresh set of loop problems leaving there. So
Okay.
yeah, yeah, cool. You don't need to hang around anymore unless you want to ask me questions.
I do.
Yeah.
So when you're doing stuff like this, are you like when you actually do specific problems, are you using a specific number set like the integers or the complex numbers to see like what it does to them, or is it just more abstract than that?
So for like
how it can
so most of the so what I've been doing lately with graphs, you deal with a loop, you make a graph from that loop, so you just deal with something like that. And then you take a look at properties and compare them to, what properties might be shared across these. Like recently, me and Lindsay K finished like this, if there are these 3 different kinds of graphs, you can prove they're all isomorphic under this condition.
Okay.
And so, but the other project I did concerning rings, it looked more like you did have a commutative ring, right? That you used when you made like a magma ring or something like that. And a lot of that came down to all you need is a commutative ring, and then you play with the equations. Remember I said there was a little bit of work to get the bilinear forms for them. But once you get the bilinear forms, it's again just playing with the equations to prove that, hey, given this amount of structure, I can prove that I also have this structure or something like that.
Following question, what do you dream about if you dream? Loops?
What do I dream about? I dream about being able to wrap up that commutant problem.
No, I mean
because-
like truly dream when you sleep.
Oh, I don't know. Actually, the other night I had a dream that there was nuclear war, and I didn't love that. I didn't love that.
That's what I was thinking.
nuclear with solar there.
Oh, that'll get us.
Nuclear war. That nuclear.
That is-
Oh, how do you
Thank you.
pronounce that word?